GPT-4, etc., have not touched cryptography at all. AI can do a lot of things that humans can do, but humans cannot break encryption schemes like the AES, and neither can deep nets.
Welcome, everyone, to the Cartesian Cafe. I am your host, Tim Nguyen. Today, we're very lucky to have Boaz Barak here with us. Boaz is a professor of computer science at Harvard University, having previously been a principal researcher at Microsoft Research and a professor at Princeton University. His research interests span many areas of theoretical computer science, including cryptography, computational complexity, and the foundations of machine learning. Boaz serves on the scientific advisory boards for Quanta Magazine and the Simons Institute for the Theory of Computing, and he was selected for Foreign Policy Magazine's list of 100 leading global thinkers for 2014. Welcome, Boaz. How are you doing today?
Great. Thank you for having me.
Thank you for coming here to have this conversation. Maybe we can start out by you giving us a little bit of a background on your career trajectory. I've interviewed people who are researchers in both academia and industry, but you're the first person who seems to have navigated back and forth between the two. So I'm curious about how that came to be and what perspectives you have about research in academia versus industry.
I didn't intend to go to industry initially. I started, I didn't also intend to go to academia even. So during my undergraduate studies, I was basically doing math and philosophy. And at some point I started with computer science, mostly because I thought it would be a good career. But then I kind of fell in love with the more theoretical aspects of computer science. And I also realized that working for a living might not be the best thing for me. I'm not that good at having a boss and taking orders. And I was doing an internships in IBM Research, and my mentor there suggested to me that maybe I should go to get a master's degree. And in Israel, a master's degree was kind of research focused and funded, so you get a stipend. So I went to the Weizmann Institute, and I think the first course I took in Weizmann was Cryptography by Oded Goldreich, and I really fell in love with the subject, and Oded became my PhD advisor, and then I transitioned to the PhD program and basically went on the academic route. And I didn't intend to move to industry, but for both personal reasons, living in Cambridge was somewhat better for me than Princeton, and also I was quite excited by this new lab that Microsoft Research was opening, the Microsoft Research New England, which has a very, very academic feel. It still does. So I was tempted by that and joined Microsoft Research, where I kind of liked it quite a lot, in the sense that you get a mixture of people that normally would be in different departments in university, and were sitting one next to each other. So that lab had economists, anthropologists, and computer scientists, and so it was a lot of fun. But at some point, I did miss students. I decided to go back to academia.
Oh, wow. Okay. I never thought of maybe students being the main reason for going back, but I guess there are many reasons. I figured that maybe the intellectual freedom or of academia, and maybe the less freedom in industry might be the more motivating factor.
Yeah, I mean, in Microsoft Research, I have to say that I think also now, but definitely at the time that I was there, I had a lot of intellectual freedom. So as far as I know, almost nothing that I did really helped Microsoft's bottom line, and there wasn't really. I was given a lot of freedom to do research on the topics that I cared about. So
Yeah, actually, on that note, I feel like how I say. I mean, there are, I guess, ways to mentor people in industry through internships and whatnot, but I guess it's not quite the same as a formal supervisor over the span of 5 years and the
Yes.
close relationship, right? Yeah.
Yes. Yes, exactly. So you kind of get like a taste of that, but not, you don't really get to see people grow. And the nice thing about university is that you get kind of to see, you have a lot of impact on people at the maybe most important stages of their career and life, and both on the undergraduate and the graduate level. And it's, and you also learn from the students, and I find it, I don't know, I feel like it keeps me young. So I like this environment.
Yeah, it's interesting because I've heard a lot of good things about Microsoft research in terms of the freedom there. If you had the same level of supervising ability at Microsoft Research, would you have stayed at Microsoft Research? Was that really the main breaking factor?
I mean, to maybe to some extent, I mean, I think there is a nice thing about, so at Microsoft Research, I really wasn't pressured to contribute to Microsoft, but I felt a little bit guilty about that because in some sense, I am part of this company and I don't feel like I'm contributing as much to this company as someone that is, shipping software, because that's really what's the main mission of the company is. And although my manager was very good at shielding me for that, like just personally, I felt a little bit, like I'm not as contributing. And while here, the nice thing in the university is that the thing that I care about, which is research and education, are the goals of this university. And if there is a mismatch and the university is not behaving according to these goals of promoting research and education, they should feel guilty, not me.
I see.
I
see.
That's very...
Yes. Yeah, that's interesting you said it, because I guess, if you're in industry, if you're in the right situation, you can, be aloof and do whatever you want. But I guess what you're saying is that even if that's the case, if there's any kind of misalignment between the company mission and what you're doing, that creates enough of a psychological cognitive dissonance that you're better off being in a aligned situation.
Yes. Yeah, I think so. I mean, maybe just me, but I feel like, here I kind of like the fact that this is basically, who knows, no organization ever behaves exactly based on following its stated mission, but at least I like the fact that I'm aligned with the stated mission.
What about this sort of, I don't know, myth/fact? I don't know. I think it depends on the situation, but professors nevertheless being beholden to chasing grants and things like that, so that there's limitations in terms of freedom for that purposes. Whereas inside a company, you're much more well equipped with resources, at least if you're aligned with the company, right? Do you have any thoughts on that?
I mean, I think, definitely professors, I don't view, grants, yeah, like it's not fun. I actually have a grant that I need to, I have a grant proposal I'm working on and I'm going to submit in 4 days. I couldn't say that it's my favorite thing to do, but actually like the type of grants I tend to pursue are from organizations that like the National Science Foundations or Simons Institute, which I'm very grateful for because they are relatively flexible. They want to kind of a broad outlines of the projects, but don't ask you for, deliverables. And they understand that when you're doing basic science and curiosity-driven research, then you might not do exactly the thing that you come produce at the end might not be exactly the thing that you planned, maybe even better, but it's often could be different. And so, well, it's never fun writing grant proposals or grant reports. I don't view this as the main disadvantage. I mean, like the one thing is that somehow, the students is a blessing and a curse, because in a sense it's a blessing because I really like working with them, but it does take a lot more of your time. And I feel like I'm, probably much busier today than I was in Microsoft Research because there are students, you have to write them recommendation letters, you serve on committees and all of those things. So, yeah, but maybe if I had like a very large, the type of research that I do is more like in small groups. If I had like a a huge lab with 40 students and 5 postdocs, then probably I would have had to invest much more in constantly writing grants.
I see. Okay, great. Maybe one more biographical question. So you're an Israeli, right? And therefore you had to do some military service as required for males in Israel. Okay, would you like to comment on that? What was the experience like, and what effect did it have on you in terms of your outlook on life, both inside and outside of science?
Sure. So I mean, I was very much not into the military as a kid. I'm still not into it, and basically any kind of so there are some opportunities in Israel, in the Israeli military, to do things that are kind of in the intelligence, more advanced, that take advantage of your academic skills, or sometimes that you could study in a university before you go to the military. But all of those things require you to sign up to do more military time than the 3 years, which was already much more than I would have liked to do. So I didn't sign up for any of that. And because of my bad eyesight, I also wasn't eligible to be a combat soldier or something like that. So I was basically a clerk. And yeah, I guess I kind of really learned about myself again, that I'm not so good at taking orders, and that so probably the military is not for me, and that by the time these 3 years were over, I was really ready to do something intellectual and actually use my brain. So.
Okay. So you couldn't pull an Einstein and be a clerk with working on
The pattern
foundations of physics, in your drawer or something like that.
No, it was more like basically the military human resources things. But sometimes you're a clerk, but you're doing this clerkship in a tent in the middle of the desert.
Okay, because there are these rare stories where people did creative work in the military, right? Like for example, Schwarzschild physicist found the first solution to Einstein's equations during his military service, right? So
I guess there are smarter people than me, and I also I didn't really do any kind of academic courses or something before the military. So I had a high school education, but I really got in. My main learning about science, etc., university level courses, was only done at university after the military.
I see. Okay, great. Well, thanks for sharing the details about that. Anyways, why don't we go ahead and get started with the main conversation of today? So so Boaz, you're a world expert in cryptography, and so that's what we'll be talking about. On my end, I've basically never studied the subject up until preparing for this podcast, and fortunately, you have a very nice book on the subject, which helped me prepare for this, and it's really a fascinating subject. Maybe can you give us maybe your overall thoughts, like a bird's level eye view of the subject before we dive in? Like what's interesting about it to you, and how do you maybe think about it?
So there are several things that make cryptography different than maybe other branches of science. So one of the things is that cryptography had a very long history of being broken, of basically people trying to design encryption systems and then not realizing that there are ways to break them, and then eventually those got broken. But then once we move to basing cryptography on more mathematical basis, then suddenly the history of cryptography became something else, where basically we could do amazing things, that not simply design encryption schemes that no one knows how to break, which we did, but also do things that are not even like public key encryption, fully homomorphic encryption, zero knowledge proofs. All of those things are things that people didn't even imagine. So this is something I write in my book, that if you're talking about, say, going to the moon or heavier than air flight, these are things that appeared in science fiction and people dreamt about before they could do this. But public key cryptography seemed so crazy that I think no one even dreamt that they could do it. And similar things for fully homomorphic encryption, zero knowledge proofs, and the other things in cryptography. So a lot of the time what we learned in cryptography, and it took us a while to do that, is to dare to imagine that something is possible, and to believe that if something is not proven impossible, then it might actually be possible. In that sense, it's a little bit like what's going on now with deep learning, where it used to be maybe the case that it was kind of in a pessimistic setting, the most things don't work, and the default assumption is that nothing works. And now suddenly we have switched into the case that everything works, everything surprises us for the better, and the main, and again, like the main way to fail is a failure of imagination, that you don't dare to do something, and because you don't believe that it will work.
I see. So it's overall cryptography is an optimistic field, I guess.
I mean, to some extent, I mean, it's kind of a combination, because you're somehow optimistic in the things that you can construct with the kind of base assumptions of cryptographers, is that something not proven impossible, then it's possible. But on the other hand, you have to get a very pessimistic mindset and think of the adversary, and think and really rigorously define what it means to be secure and how your systems can be attacked. So I would not say like that cryptographers are. So cryptographers, I guess, oscillate between imagining amazing things and trying to break them, and finding like very subtle ways to break.
Yeah, it's very much like a game theoretic way of thinking, as we'll see shortly. Why don't we start out by actually let me give my take of a bird's level eye view, maybe, and then you could comment on that, and then we could start maybe writing down a summary of what we're going to talk about, and see how far we get with that. So I think the way I think about this is that the setting we're in is we're concerned about privacy and security, specifically in the context of communication, right? Because you can think about privacy and security in other ways. Like if you're a hermit and talk to nobody, then you'll have privacy. And for security, you can hire a bunch of bodyguards. That's another kind of security, but that's not the kind of privacy and security we're interested in, right? We're trying to communicate messages, right? And so privacy, right? We can think of that as secure.
And by the way,
communication.
I would say it's now beyond just communication, but also computation.
Okay, we'll see why that's a qualification. Yeah. Okay, great. So privacy is secure communication, and then I would think of security as basically protection from, say, observation, theft, attack, etc. Right? Basically anything that would compromise that communication. So that's kind of the setting in which we're working.
Maybe you want with privacy, maybe change secure, because secure seems like security, to secret, confidential.
And the reason why this is, maybe this is just worth stating, even if it's obvious, right? In the modern world, we're one large communication network, right? And so we need to preserve the integrity of the system because there are so many interactions that occur. And that's why cryptography is so important. Do you have anything to add to my amateur summary here?
No, I mean, I think you're right. And one thing that we should really emphasize is that cryptography is really important, even if you have nothing to hide. So even if you say, I don't understand, my life is an open book. I don't do any crimes. I don't do anything that I'm embarrassed about. So why should I care about cryptography? But even if you say, for example, you definitely care about, say, you might not have any things you're embarrassed about, but you still have a bank account and you would like to keep its content with you rather than someone else. And you still are using various devices that you don't want to have, say, malware or ransomware installed on them. So you want that when you get an over-the-air update, then it will be authenticated. So you're sure that it actually came from the company that you went to, when you browse the web and you go to a website like CNN and you see the news, you do want to make sure that you actually see the right news rather than someone sitting on the router between you and the CNN server has modified the web page and show you something else. So all of us, even people that have no secrets, do need cryptography in today's world.
Right, and I guess that falls into what I wrote here in terms of security, because I guess that right, you're preserving the integrity of the communication channels. Yes. Yeah. Okay. Great. So why don't we maybe start? I'll start writing an outline of what we hope to cover. We'll see. It's pretty ambitious, but it's always good to be ambitious. So I think as the first thing we'll talk about, let's do a warm up, and we'll play with some examples just so to whet people's appetite and just to get a feel for why cryptography is hard, right? So why cryptography is hard, and then we'll from there go into the first major subject in cryptography, which is private key cryptography. And here, what this means is that there's a notion of a key, which we'll get into, but here the essential feature is that there are shared keys, right? So you and I have the same key, right? For which is pretty intuitive, right? Just like an ordinary key to a door, right? There's one key that works, whether it's you or me, right? And just from having studied your book, I think here the main result that enables the cryptography here and elsewhere is something called the cipher conjecture. Right. I think you said in your book that's not a standard name. I don't know if you want to give it another name for context.
Existence of one-way functions.
Okay.
Pseudorandom generators. So these are known to be equivalent. It's not a trivial result, but okay. So the most standard name for this is like existence of one-way functions, and this is known to be equivalent to existence of pseudorandom generators.
I see. Okay. And I guess we'll get there. But I think the key thing here is that this result and many others that are either equivalent or consequences of it thereof fundamentally relies on, the status of whether P is equal to NP, right? So yes. That's the whole business kind of hinges on this. Okay, we'll get there, but I just want to kind of give a roadmap that there's sort of like some milestones here that I think are fundamental. And then from there, most of the heavy lifting, I guess, is done once you've studied private key cryptography, and then public key cryptography is, I mean, it's of course very maybe non-intuitive or surprising, but sort of I think a lot of the work has already been done once we've done private key cryptography. Is my sort of sense. I don't know if you have any thoughts on that, but this is where now the keys are, we have asymmetric keys. Let's say, let's call it that. Yeah. Anything to add to the outline so far? I've just sort of been talking.
That's good. That's good. I mean, I think we'll mention probably the one-time pad when we talk about private key cryptography. And yeah, I think I agree that in terms of definitional work and understanding the notions of security, a lot of the work is done in private key cryptography before you get to public key. In terms of the actual mathematical constructions, they tend to be quite different, and they use different types of math.
Yeah, but right. In terms of just the fundamental notions of security, it's sort of done with the private key setting. And then to wrap it all up, we can talk about applications. Right. So things like say Bitcoin, authentication that you already mentioned briefly, and then possibly applications to machine learning. Right. All right. I think we have a lot of topics here. Let's see how far we get. Okay. All right. So this is now our warm up here. I could talk about it, but I guess maybe you want to go ahead and talk about what this contraption is all about and how it's used to encrypt and decrypt messages.
Sure. So maybe we can even start with the even more basic thing, which is the substitution ciphers. So basically, maybe that's the first thing when people try to encrypt messages. then the first thing they had in mind was something like something like a table where A, B, C, D, F, G, H, etc., and gets mapped to some. Each letter gets mapped to another letter, and maybe maybe A gets mapped to I don't know, age, and we can keep it in order. B gets mapped to I, or we could do some other things, but there is some kind of a table that maps one letter to another, and that was basically maybe the first type of cipher that I think was invented and reinvented over history. Both parties would have some kind of both parties would have some kind of a table like that. Sometimes they use some kind of a short phrase or number of the offset to remember it. And then they just translate their message according to the table by replacing each letter by the letter that corresponds to the corresponding one. And this cipher can be broken by what's known as frequency analysis. So basically, for example, in English, the most popular letter is E. So if you get a long enough text and you see, maybe I'll continue, and you see a lot of L's in it, and you can, then if it was done by a substitution cipher, then you can guess that maybe L corresponds to E. And then you can start using some other statistics. Maybe you know that E often comes with the triple THE, or you can use some other frequency, and pretty soon you can break and you can recover this. And this has been the case time and again. One of the stories that I have in my book is the sad story of Mary, Queen of Scots, who was plotted some attempt to free herself and assassinate her cousin using this substitution cipher, which was broken by frequency analysis, and then she was executed. So what we see here is this Viginere cipher, which is basically a more complex version of substitution cipher. And the basic idea in Viginere is that it's like we have a collection of substitution ciphers. So we say the first letter uses this table, and then the second letter might use a different table, and the third letter might use yet a third table. But you cannot have an infinite number of tables. So at some point, you go back and reuse the table. So if, for example, you have 5 tables, then every 5th letter uses the same table. And this can be enough to kind of erase the statistics. So if E is the most popular letter, then if E is if suppose the key is you have 10 different tables, then only 1/10 of the time E is mapped to 10 different letters, and that kind of really averages out these kind of spikes. And so you basically get a much less spiky distribution of frequencies, and therefore frequency analysis, at least one without use of computers or without using a lot of text, becomes very hard with Viginere, which is why it was kind of considered an unbreakable cipher. At some point, there was even a word for it in French, which I cannot pronounce, but basically that it's an unbreakable cipher.
Mm. But what year was this? Do you remember?
So Babbage cracked the Viginere in 1854, but didn't publish it. But in 1863, Kasiski broke Viginere and did publish it. And the Confederates used the Confederates used this kind of contraption where basically each table was obtained by kind of a shift of by a different shift, and you would rotate the inner circle to create the table, and they used the Viginere cipher, and they thought it was unbreakable, but it turns out it can be broken, and the idea is kind of simple. First, you guess the number of tables, the length of the key, which given realistic limitations on how many tables and how long of key you can replace, it wasn't that long. It was maybe a number between, say, 5 and 15. And once you guess that, then you can basically just do frequency analysis, but do it, say, on every nth letter, where n is the length of the key. And you can then very easily test your hypothesis for the right, whether you got the right length or not. And once you got it, then you got it, and you can recover everything. And this is what Union officers did, and they routinely broke the communication of the Confederates. 80 years later, the same story with much more complicated systems on both sides was repeated between the Nazis and the British in World War II and the Enigma.
Actually, maybe can you say maybe a word about that? I mean, there. I see. Are you saying that the same method of basically statistical analysis allows you to reverse engineer kind of what the encryption protocol was?
So in the Enigma, it was much more complicated. So the Enigma, you can also think of it as a substitution table, but where the number a priori there is kind of huge exponential number of tables, because it was kind of like a typewriter where every time you press on a key, a set of rotors move that determines the permutation between that determines the permutations between inputs and outputs, and there was the number of permutations between letters is kind of like 26 factorial, which is an immense number, and the Enigma had something like, not that far from it, a number of ways to set the particular rotors, and I forget, maybe it's 10 to the 40 or some huge number. And so you really had to understand the structure of the Enigma to break it. So it really required much more sophisticated mathematics. And initially, the Poles, the Polish intelligence, were the first to make some breakthroughs on that. And then the British kind of took it to the next level, and eventually they mechanized this process in Bletchley Park, and Alan Turing was heavily involved in that, and they found ways to mechanize it so that they could break the Enigma on basically a regular basis.
Now, the amazing thing is, did they actually have to, I don't know, obtain a physical copy of the machine, or was it purely mathematical analysis?
So at some point they did obtain, I think, some physical copies. I think they got pretty far also maybe before it, or they had like very earlier machines. I think it's kind of a complex story, because the Germans at some point switch machines or switch settings of machines there was like a Navy machine which had more rotors, so it was more secure. So so it was combination. I think the Enigma itself was based on some cipher that was constructed before the war by some Germans, so they had some idea of the rough operation.
Well, I think that's a very interesting story.
There is a lovely, by the way, if you care about the history, there is this really lovely book, The Code Breakers, which kind of is all about the earlier history of cryptography.
So, all right. So now that we have this warm-up example of an attempt at a secure way of sending messages, alas, not so secure because it was easily broken. I guess we can see how difficult it is to come up with a secure encryption system. like many things in mathematics, one of the hardest steps is to find a good definition, right? Because we just have one toy example. We could have listed maybe 100 other ones, and it's sort of like this, like, I'm just going to come up with something which I think is hard, but if that's not quantifiable, then someone very clever, more clever than you, could just break it, right? And so I think it's important to try to find a good definition. Let's go through that. So Boaz, maybe let's walk through the logic of trying to find a good definition of security.
Yes. So I think before we even talk about security, let's maybe define what kind of a mathematical object an encryption scheme is, or at least a private key encryption scheme is. So we generally think of, right, we have two objects. We have the encryption algorithm and the decryption algorithm. So the encryption algorithm generally will take, say, a plain text. So this is the message that you want. So this is the set of all plain text, and it will also take a key. And of course, I should make some room. And it will transform this into a cipher text.
Right. So plain text just means that the text is itself the message. You can just read it plainly. And the
Right.
ciphertext is the encrypted message, the one that's hard to make sense of.
Right. Right. And generally, we in computer science, we often assume everything can be encoded in everything can be encoded as just strings of zeros and ones. So we can think of this as some 0, 1 to the L times 0, 1 to the N maps into some 0, 1 to some I don't know, let's call it T. So this is the encryption algorithm. And this and the decryption algorithm, right? So this is encryption. And decryption needs to do the reverse operation. So it's an algorithm that takes as input the ciphertext, right? And a key. And maps it back into the plain text. We can think of it as mapping 0, 1 to the T times 0, 1 to the N to 0, 1 to the L. The key property that we want from an encryption is, first of all, before we talk about security, is validity. So validity is basically that if we encrypt a message, so that for every message, say X, and for every key K, if we encrypt the message with the key K, and I'll use the key as a subscript, and then we decrypt it with the same key, then we get the same message back.
And just now that we have the example from the previous slide, the key in the case of the Viginere cipher is basically the collection of tables that you used, right? It's the auxiliary information you need to do the encryption process, and
yes,
once you have that, then you can encrypt and decrypt.
Exactly. So now we have a definition of what kind of an object is an encryption and decryption scheme. It's a pair of functions. So encryption maps a plain text and a key into a ciphertext, and decryption maps a ciphertext and a key back into a plain text. And we require this notion of validity, and now we can just start talking about what it means to be secure.
Sure. Maybe just one last thing. So this is, as we mentioned in the outline, this is private key cryptography, yes. Right? Yes. And it's, again, referring to our, I guess we'll use that as a recurring example, the Viginere cipher. It's clear that you want to keep the key private, right? Because as soon as the key is exposed, then you've exposed the algorithm. So it's necessary. It's absolutely necessary that the keys remain private.
Right. Yes, and actually, this might be a good point to mention what parts of what is secret and what is public in this scheme. So basically, one of the things that we want to say is that the only thing that's secret is the key. So this is known as Kerckhoffs' principle in cryptography, which basically says that we cannot hope for security by obscurity. So the idea is that if we are going to use the same the encryption, we are going to use encryption for an extended period of time, the only thing that we can refresh is the key. So we should not assume that our adversary doesn't know the details of our algorithm, because eventually the adversary will learn the details of our algorithm. So so I've been told that one version of this was that in the NSA they had this this saying that basically you can assume that whenever we build an encryption device, the first copy of it is shipped to the Kremlin. So basically, the only secret, the system should be secure under the assumption that the only part of this the only part of it that is not known to our adversary, the one that's trying to break it, is the key. And what does it mean that the key is not known? That basically the way we say it is that the key is chosen at random. So we fix everything. We fix the encryptions, we fix the decryption, we are given the message that we want to transmit, but the key is chosen completely at random and then shared by the two parties because this is a private key encryption.
Right. I guess the analogy would be like a password, right? You don't want your password to be a function of some obvious attributes of you or just some globally known constant like password, right? It should be random, right? And
yes.
It's the
So the
same
password
principle
should be random, and you don't want the security of your the security to depend on the fact that your adversary doesn't know if you're using Chrome or Safari. So that you should assume that whoever is trying to attack you knows which computer you have, knows which browser you have, maybe knows what time of day do you usually log into your account. So those things are not secret. The only thing that protects you is the password.
Right. And going back to this optimistic versus pessimistic, I think that the thing with cryptography is that you basically have to always steelman your opponent, right? And that's something that outside of cryptography, that's something people aren't typically good at, especially in politics. But but in cryptography, the key is to steelman your adversary, and in this case, it basically means they are as smart as you because they have exactly full knowledge of your algorithm. The only thing they don't have is ownership of the key. So basically, it's privacy through ownership of who owns the key.
Yes, and in fact, you really in cryptography often kind of super steelman your opponent in the sense that you assume that your opponent has much more, say, computational power than you, because if you think about actually using cryptography in practice, every time we go on the web, we are using encryption and decryption. So this has to be very computationally efficient operation. Encryption and decryption itself has to be done very computational efficiency because we do it all the time. But the adversary might only be interested in a very particular message, so they can invest a lot of computational resources into breaking that message. So we often want we want breaking the encryption to be much more difficult than using the encryption.
That's a good point. Yeah, you are super steelmanning them. Okay, all right. Well, I guess we'll see that soon enough. Okay, great. All right, I think we do have the foundational definitions down now. I guess maybe we can start going to the notion of security that you alluded to, right? Yeah. Okay. Great.
So just so we remember the notation, and now maybe I'll ask you, how would you define security?
Let's see. So I did look at your book. So I'm not a completely naive person, but I know in your book you basically I think went through something like 3 putative definitions of security, and we could just kind of go through that, and I can play sort of like the the ignoramus going through each one of those.
Yes.
So I think I'll call this like first attempt.
Maybe actually, like even before that, maybe we should introduce our cast of characters. Alice, right? So we'll have Alice, Bob, and Eve, and Alice and Bob share a key, and Alice has a message she wants to send to Bob. So Alice is going to send the encryption with the key of X. So Alice knows X, and Alice is going to send a message encryption with the key of X, and the goal is that Bob can, of course, decrypt it, but the goal is that Eve doesn't learn about the message or doesn't recover the message. So this is basically our cast of characters, and now we can try to define what it means to be secure.
Right. So basically, Eve can see right. So Eve can see Y, the encrypted message, but nothing else, right? And also Eve has full access to the function capital E as well.
Yes.
Right?
So Eve knows right. So Eve knows E, knows D, and Y.
Yes. Okay. Great. I like the naming. So like, I think I actually, the physicists also like Alice and Bob, right? A and B. So maybe that's inspired from that. And then Eve, like eavesdropping, right? So it's very it's a good naming. Okay. Anyways, okay.
This is not my invention. This is pretty standard in cryptography.
Yeah. But it doesn't seem like a coincidence that, when physicists have these sorts of thought experiments, it's always Alice and Bob as well for A and B. Okay. Anyways, so let's do the first attempt, according to your book, at least. So the first attempt was something like the following. It's hard to write the full thing in all mathematical notation, but hard to recover the key, right? Mm-hmm. So in other words, basically the probability of, guess the key should be basically 2 to the minus n. Basically, there were, so let's back up. So the keys, we said, were always in the set of n possible bits. So there's 2 to the n strings here. And our first attempt is to say your scheme is secure if you have you can't do better than random guessing to figure out the key, right? Mm-hmm. I think that was your first definition.
Yes.
Yeah. Yes. Now let's take a look at this definition. I think the peculiar thing about this definition is that it says nothing about recovering the message.
Yes.
Right? I think like the original intent of security was to hide the message. Of course, you want to hide the key too. So I'm just sort of like looking at this as with attempted fresh eyes. There's something a little bit funny about this definition in terms of keys and messages. I don't know if you want to follow up with that, but that's like sort of the first funny thing about this definition.
Yes. So in one thing, like the definition seems like basically the precise number 2 to the minus n, but somehow it does seem like some kind of a necessary condition for security, in a sense that because we know that if you do recover the key, then you can decrypt and recover the plaintext. But it's a necessary condition. It's not a sufficient one. And in some sense, this is a kind of a counterexample would be the following. Think of encryption with a key k of x as just being x, and decryption with a the key k of y just being y. So just the identity function. So this is a valid encryption and decryption because whenever you encrypt and decrypt, you get back the same thing. And it satisfies this definition because you give no information at all about the key. So Eve would not be able to guess it better than random chance, but it is obviously completely insecure. You're just sending the message in the clear. This is the least secure encryption possible. So that shows that this is maybe a necessary condition, but it's not a sufficient one.
Indeed. How do I say it? This is a very common thing in mathematics. You try to write a reasonable definition, and then you find the most trivial counterexample, right? The edge case in this case, and this is like a very extreme example, but it does highlight the reason why this is a bad definition,
Yes.
even if it might not be obvious at first, right?
Yes.
Great, great. Okay, so now we know that this first attempt is no good. Now, from this lesson of the failure at the first attempt, let's try to do a second attempt.
Mm-hmm.
So the second attempt is basically, let's just replace the key in the first attempt with the message, right? So it should be hard to recover any message. The message has L bits, and so I guess what the probability that Eve can guess a message is what, basically 2 to the minus L, right? Random guessing.
Or let's say even we can even be we'll see, like we can even say 2 to the minus n with an I towards the next broken thing. So if you know, if for example the key is shorter than the message, which sometimes happens, then we cannot hope for better than probability 2 to the minus n, because you could always guess the key. But definitely, let's say 2 to the minus n would still.
Or should we? Or should it be, maybe, are you saying it should be the minimum of n and l? Is that what you're trying to say?
Let's assume L is bigger, because that will also be for us less later.
Yes, yeah. I mean, that's sort of reasonable that L is bigger. Like intuitively, the set of keys, your key should be shorter than your message.
So one observation can always guess message with probability 2 to the minus n, and that is basically by guessing the key and then decrypting.
Ah, that's right. Basically, this is try all possible keys.
Yes, try all possible keys, or try a key at random, and just so we cannot hope for better than probability 2 to the minus n. But this is fine. Like you know, even if it was 2 to the minus n over 2, that would be fine, because you know, these would be exponentially small probabilities. So we are not that worried about that. First of all, we have no choice. We have to be comfortable, because obviously you can always do it. But second, even if the key is moderately long, like 128. So you know, the chance that a key of say 2 to the minus 128, if you do the math, is say I think say 2 to the 128 is I believe larger than the number of milliseconds that have gone between the Big Bang until now. And in one of those milliseconds, there was the meteor that say destroyed that killed all the dinosaurs. So in some sense, this is a high. The 2 to the minus 128 is larger than the probability that a meteor of the same type that destroyed the dinosaurs will land on both of our heads in the next millisecond. The first definition was too weak.
Mm-hmm.
Now this definition, in some sense, it's too strong or impossible. And let me explain why it's impossible.
Okay.
And there is something that's maybe always useful in mathematics, but really, really important when you're talking about when you're talking about in cryptography, which is whenever you write a probability statement, you have to know what is the probability taken over, what is the randomized experiment or the sample space that this probability is taken over. And here, right, this basically has to be probability over choice of key. That's the random part, right?
Okay.
But the message itself, we didn't describe any probability distribution over messages.
Okay. Mm-hmm.
So it kind of doesn't make sense, because what if the message, you know, I mean, what if the message was, say, X was a random English sentence?
Mm-hmm.
Then the probability that Eve can guess a random English sentence is the probability that Eve can guess a random English sentence will not be 2 to the minus 128.
Right, it'll be much lower. Right.
Much higher, like much better, right? Because like let's say a random English sentence of like of 5 words or something like that, something that's like
Oh,
like say
okay.
random English word. Let's say you know, maybe we're just trying to know if Eve is saying attack or retreat.
Okay, I see. Okay, if you have a bound on the message and it's not too large, okay, yeah, then it'll be higher. Yeah.
Yes.
Mm-hmm.
So to make things formal, and is we need to do 2 things. One is define a prior distribution on the messages, because otherwise the probability doesn't make sense.
Mm-hmm. Yep.
And the second thing is replace 2 to the minus n needs to be replaced with something that has to do with prior.
Mm-hmm.
So
I
maybe
see. So yeah. Okay. So you're saying that the problem with this second attempt is it has nothing to say about the distribution of messages. Is that right?
right. Yes. So basically what we want is some kind of a experiment like the following. X is say sample from some probability distribution M probability distribution on messages. And then we could hope that probability over both the choice of X from M and the choice of key from 0, 1 to the N, that Eve guesses X is at most, and now the best possible guess for Eve would be the maximum over some X hat probability M equals X hat. So we could say we could say this is the best you could do. And this is the definition that Shannon came up with, or this is equivalent to the.
I see. I think it might be helpful to make this a little bit more concrete. And one nice thing you highlighted in your book is that you can reduce an equivalent definition is in this is in the binarized setting where
Right.
if you where you just pick 2 messages by flipping a coin, essentially either 50-50 chance of picking them, and you can reformulate in terms of that. Did you want to maybe flesh that out just so it's a little more concrete? Yeah.
Sure. So let's so here is a special, but we'll see it's not so special case, or maybe we'll say just not a so special case. So where we say M is just 2 messages, so just the uniform distribution on 2 messages, x0, x1. And then the probability, what we want is that the probability that X, when it's chosen at random between x0 and x1, and the key is chosen, say, at random in 0, 1 to the n, that Eve, given encryption k of x b equals xb, so b guesses the right thing, maybe x is at most half. So basically, if a priori Eve knew that the message is either attack or retreat, and it's with probability half, then the posterior distribution, the posterior probability of Eve after seeing the encryption has not been changed. So Eve learned nothing about the message from the encryption, from the ciphertext.
There's just one technical. Should this be equal to a half just by symmetry, or?
I mean, yeah, you can always guess half. So I mean, unless Eve is really stupid and say she knows it's either x0 or x1, but she guesses some
I see.
different thing.
Got it. Okay.
But for any reasonable Eve, it would be exactly half. Yes.
Got it. Okay. This is just to allow for this for any like Pareto suboptimal strategy, basically. I see. Okay. Yeah. Okay. Now I'm recalling why that previous definition was bad. I guess let me just go back one slide and take a look at what I wrote there. So the problem there was that we didn't quantify over the space of messages,
Mhm.
right? And as you explain in your book, you could just get lucky with your decryption scheme. The equivalent of this would be like you have a password, and I could just guess your password, and it
Yes.
has nothing to do with the keys or how hard the encryption or decryption scheme is. If my strategy is I'm going to guess that your password is password, if you happen to have the password, then I win, and there's nothing else to say about that, right? So there has to be some notion of randomness in the messages. Otherwise, this definition is, as you wrote here, for security impossible, precisely because of the example I just gave.
Yes, and it's also kind of important in some sense if we basically are we have a universal quantifier over the probability distribution of messages, and that basically means that we are we don't know what is the prior information that our adversary has, maybe through some other means, about the messages that we may send. So one example for was that the Germans in World War II, they always started the messages with Heil Hitler, because that's the way they started all of their communication, and the British knew that, and it actually helped them. It provided something useful that helped them in decryption. Now, if the encryption scheme had perfect secrecy, then basically it should say that any prior knowledge would be useless. You would not, no matter what prior knowledge you had about the distribution of messages that Alice might send to Bob, seeing the ciphertext would not allow you to update your knowledge, and your posterior will remain the same as your prior was.
Yeah, let me make a few comments about this. So I think, so one thing I noticed, for example, with in terms of this thing you wrote on the right-hand side there, I think this is a more general, I don't know if it's just apparently more general or it actually is more general, but it's more general than what you had in your book, because I think in your book you only talked about uniform distributions.
Yes.
Right. So I think it is slightly more general, but okay, it still makes sense.
Yes, but it is equivalent. So in my book I have this theorem showing that two messages is equivalent to any uniform distribution, and you can also generalize the same proof to show that it's also equivalent to any distribution. So
okay, I see.
You can prove that the special case, that if an encryption scheme satisfies the special case that I put below, but for every pair of messages, then it has to satisfy also the condition that I put above. And I think it actually might not be useful to go over the full formal proof, but I can give you the intuition why this is true.
Sure.
And the intuition is the following. If there is any difference at all, so maybe the way to think about it is, so basically for every fixed x, you look at the distribution on that is induced by basically taking encrypting x with a random key. So this is a distribution over ciphertext.
Yep.
Now, suppose that there existed two x's, x0 and x1, where the two distributions were not identical to each other. Then basically you could show that you could get probability better than half as an adversary, because there is some element that is a little bit more likely under one of them than on the other. And if you see that, you will guess it came from x0, and otherwise you'll say it came from x1. So basically, the condition, the special case condition that for every pair of messages you cannot guess better than half, implies that for every message x, for every message x0 and x1, the distribution induced by x, and the distribution induced by x0 and the distribution induced by x1 is identical. And if the distribution on y is identical, irrespective of what x was, then basically Eve doesn't learn anything.
That's right. Yeah.
So this basically corresponds to Eve basically learning nothing about the message, given the ciphertext that she didn't know before.
Yeah, as I was thinking about this, I really like this way of thinking. I mean, the sort of the the analogy I have in my mind is basically no matter how biased or how idiosyncratic or how quirky you are with choosing your password, I don't gain anything more than knowing that quirkiness. So for example, if I knew your password was like a food item and a number, like pizza 7, okay? So that definitely reduces the space of all possible passwords to, you know, an order of like, I don't know, let's say like 100,000, because there's like roughly 10,000 words in the English language. Some of them are going to be food, and then times a digit, which is like 10 possibilities, right? And I could list all the combinations of food and number, and then even if knowing that, your encryption scheme, I can't learn anything more from that than still that you chose some you know, food or number, right? Yeah, as opposed to you know, if somehow your encryption scheme was such that when I, you know, say your encryption scheme returned a string of letters. If I knew, for example, that Chinese food was encrypted with more E's than Italian food, then if I saw more E's, then by guessing that your password had a Chinese food in it, I would you know, gain more you know, have a higher probability than just chance, right?
But yeah, by the way, maybe I should, yeah, there is a nice story. I think I mentioned this in the book, which maybe I should mention it again. The interesting thing about the Enigma machine, so the Enigma machine basically, it's like a set of permutations on letters. So every time you would type a letter on this, every time that you would type a letter on the Enigma machine, then the encryption of that would be a different letter, and every time the permutation would change. But it had the property that it would never map a letter to itself. So if you wrote A, it will never give out A, which seems like maybe it makes it more secure. It could never spit out this, but in some sense it introduces a bias.
Yes.
And
yes.
In March 1941, Mavis Beatty, who was one of the cryptanalysts at Bletchley Park, she received a very long message, and she noticed that the message did not have any single L. And she realized that this cannot happen by chance. That the only way that, and then she figured out how could a message be so long and not have a single L. And so she realized that the only way that could happen is if the plain text was all L's. So she realized that it was probably kind of a board operator or some testing, or maybe trying to test the machine, and just sent out a message that was all L's.
That's you know, I would not have guessed that. You know, that. Because it requires the further assumption that that the permutation always, you know, changes the.
She knew that,
letter,
right? So they knew the properties of they knew a lot of properties about the Enigma machine.
Oh, so they already knew that one. Okay.
So they knew that property, right? So they knew the property that the machine never like the permutation has this property that it doesn't have a fixed point. It never outputs the same letter itself. So then she kind of figured out that if the whole message is so long and there is no L, it has to be the case that there was tons of L's in the beginning, and then she kind of realized that probably a board operator and just typed L just to test the machine. And then because of some other weaknesses of the Enigma, once you knew the plain text, it could really help you learn the daily key. They had like some key that changed every day, and that could really help you learn that daily key. And then that helped her to learn about a planned attack by the Italians, and helped the British get like a major maritime victory.
Yeah, that's amazing. So, you know, actually, one thing I noticed about this definition, and I'm curious which inspired what. I'm guessing, since this is an older field, that cryptography inspired it, but it looks very similar to the notion of differential privacy, right? Differential privacy says if you if you kind of remove or add an element, that you gain a negligible amount of information. It's not quite the same because, you know, there is but it's very similar. It's sort of saying you basically have minimal edge, or in this case no edge, but it has a similar flavor, right?
Definitely. And I think the people that invented the differential privacy are cryptographers. So they come from this field, and they were inspired by cryptography. So Cynthia Dwork is she's my colleague at Harvard, and also did a very strong work in cryptography, and obviously she and her colleagues were very much inspired by cryptography when they came up with this the de facto piracy definition.
You know, I'm glad you brought up this Enigma example, because at the face of it, you know, when I made this silly example about passwords and food, you think, okay, ease and food, that's such an artificial example. But I think the point now, which is more clear to me now, is that if you have any edge, that can be fatal, because you can somehow bootstrap and magnify it if you just keep I don't know, amplify it in the correct way, right?
Yes. And I think especially in today's world where you have, you know, a lot of there's lots of communication, a lot of data, and yeah, so even a minor edge could eventually accumulate and like you say, eventually be fatal. So
yeah,
you really want to make sure that you have no edge, or at least an edge that is kind of so, you know, exponentially small that it's completely negligible. That you know, even if you were encrypted as many, you know, through the age of the universe, you would not.
Sure. Yeah, maybe that's actually a good point to get into, because I think we've written this definition, and you mentioned already earlier that there's a computational caveat to all of this. So I guess there's a computational modification to this, right?
Right. So at this point, this definition can hold, and we can show that there are encryption schemes that satisfy this, and they don't need to make any computational assumptions. So we can talk about it if the one-time pad that satisfies this definition.
Mm-hmm.
So it is possible to satisfy this definition as long as you're willing to allow the secret key to be as large as the message.
Mm-hmm. Mm-hmm. Sure. Yeah. Maybe we could just look at that example, because I think this is quite an abstract definition. So let's
right.
maybe look at a concrete example. Yeah. Okay.
Right. So maybe we can do the one-time pad. So this is the one-time pad, which goes back to I think the early 1920s. It's called the Vernam cipher also. So it was invented by Vernam in 1917, and but I think Shannon was the first one that really gave a formal definition of security and showed that the one-time pad satisfies this. And the easiest way to think of the one-time pad is the very simple case where let's say that our message is only 1 bit and the key is only 1 bit also. So let's say the messages X is just either 0 or 1.
Yeah, basically I'm trying to guess your coin. You flip a coin and I'm trying to guess whether it's heads or tails.
Right, and then encryption of, in this case, like encryption of K with X is simply the XOR of K and X. So the XOR, so let's maybe write the truth table of the XOR function. So if you have A, B, and A XOR B, so let me make this a little nicer. This is the truth table for the XOR function. So another way to think about it is that A XOR B is like A plus B modulo 2. Mm-hmm. So basically, if there is a single one, then it's 1, and if there are 2 zeros or 2 1s, then it's 0. And now let's so we can define encryptions with key K of X as X XOR K, and decryption with key K of Y as also Y XOR K. And now if we just make sure that this is valid, so we want encryption of so if we want to make sure that if we say take the encryption of K of X and then we decrypt it, then that would equal to X XOR K and all that XOR K, right? And now, because this is really addition modulo 2, we have the same properties of associativity. So it's like XOR X of XOR K XOK. And now you can see that this is 0, and XOR 0 is always X.
Yes, indeed.
So this is a valid encryption scheme.
Mm-hmm.
And now we can just look at, and now there is, we can make a claim, say a lemma, that the one-time pad is perfectly secret. This is for this 1-bit version. And we can just basically prove it directly. Here, there is almost nothing, right? There are only 2 messages. So we basically just want to look at the probability distribution that induced. So the way to think about it is maybe, let's look at these 2 messages. The message is either 0 or 1. And so this is the plain text space. And the ciphertext space is also 0 or 1. And then if the, let's make the 0 key correspond to blue. And if the key is 1, let's write it as a red edge. So basically, if the key is 0, then 0 is encrypted as 0 and 1 is encrypted at 1 as 1. And if the key is 1, then 0 is encrypted as 1 and 1 is encrypted as 0. And what we can see is that the probability distribution, that if we look at the encryption of K of 0, then this is just the uniform distribution on 0, 1, where K is random, and this is the same as the encryption of 1, right?
Yep.
Wherever the plaintext is 0 or 1, for a random key, we get the uniform distribution. So you can see that basically from the point of view of Eve, she learns nothing. So
That's right.
this is basically the same condition that we mentioned before. You learn by observing Y. You learn nothing if the key is random and you observe Y, then you learn nothing.
Mm-hmm. Mm-hmm.
Now, if you were to encrypt a second, say, if you were to keep the same key and encrypt a second bit using the same key, then this is now this is very different. So so maybe we can also show that. Look, so let's say, suppose we use a 1-bit key, and then we have a 2-bit message. So let's say the message was so let's say the message was either 0, 0 or maybe 0, 1, right? Then it will get mapped to say to 0 XOK, 0 XOK, or 0 XOK, 1 XOK, right?
Mm-hmm.
And this is basically would get mapped to KK. In this case, it would make K to in the negation of K.
Mm-hmm.
So basically, Eve, by seeing if the first bit is the same as the second bit, she can learn if the message was 0, 0 or 0, 1.
Indeed.
So if you use the same, if you reuse the same key for a longer message, then you break all of the security.
Mm-hmm.
And this is why I like to say that the one-time pad is basically, it's like the name which is like point away from your gun, because it tells you never use the key more than once. Like every bit of the key should only be used for 1 bit of the message, and you cannot reuse it.
Sorry, what was the analogy you used?
Point away from your gun. Like
don't shoot yourself. Don't shoot yourself. Basically.
Yes, yes,
Oh,
yes,
I see.
basically. Like using like it's in the name. It's basically in the name. It tells you just use it 1 time, and now it might look, everything it might look here like a toy. Like basically, we are talking about encrypting 1 bit, but you can generalize this basically by just you can define the one-time pad. You can just use it if you want to encrypt longer messages. You can just have the key be so for longer messages, you can have the key be K1 till KN, and the message be X1 till XN. and you can just encrypt the encryption of with the key K1 till Kn of the message X1 till Xn is just you XOR each bit on its own.
Yep. So it's just the n copies of the one-time pad, basically.
Exactly, n
Yep.
copies. But as long as you don't, you keep the one-time pad, use it only one time. But the problem is that it's really, it becomes very, very cumbersome to have, again, like think of the modern world. We are encrypting files that are like maybe gigabytes or terabytes. We'll need to exchange ahead of time gigabytes or terabytes of keys and keep them in a secure way that they are not going to get leaked. And even so in the 1940s and 50s, the Soviets were using one-time pad for communication. And the way they were sharing these keys is by code books. And again, like the logistics of exchanging so many code books were very complicated. So they started reusing the key. And basically they were thinking, okay, we'll use it maybe for some different KGB stations in different countries or something like that, and maybe it will all turn out okay. But then basically the US intelligence figured this out, that they are reusing the keys, and they started this Venona project. And in my book I mentioned Jean Grabil, who was the founder of this project. And basically they managed to break a lot of Soviet communication because they didn't follow the instruction on the box, and they used more than once the one-time pad. And
actually,
many KGB agents were exposed because of this project.
Actually, let me clarify a bit. So you said only use the one-time pad once. So I interpret that to mean that the K1 through Kn here are all chosen independently, right? You don't want to you don't want to duplicate any of those.
Yes.
Although I think what maybe I misunderstood what you said. You can use the key more than once to encrypt as many messages as you want, right?
No.
Oh, you don't? Okay.
No, so once you've used K1, you can never use it again.
Well, what I meant is that you have K1 through Kn. Once you have that tuple that's well selected, that can be your key forever, right?
No, you can transmit n bits using it. You can transmit a message of length n, and that's it.
Oh, so you have to regenerate a key for every new message.
Yes.
Wow. Okay. Well, what's
because here, if you think of the example that I said before, like say, suppose you repeat, suppose you have this key of length n, and you repeat it for 2 distinct messages.
Yep.
And suppose that your adversary knows that there is some probability that the message you're sending the same message twice, or you're sending a different message. Then the adversary could figure out by looking at whether you're sending whether the output is 2 identical blocks or 2 different blocks, to figure out which one of those was the case. So so the adversary learns something from the ciphertext, which should never happen.
Wait, but I'm a little confused now, because I thought the point of perfect secrecy was that you don't learn anything new. So you pick the key, right, and you have 2 distinct messages. It doesn't matter whether you sent it yesterday or tomorrow.
Right. So right? you can only, right, so one-time pad is perfectly secret as long as you only use, as long as you only encrypt one message with it, which is the length, at most the length of the key. Or, if it's a sum of messages, you encrypt them with different pieces of the key, but once you run out of pad, you run out of pad. You never use it. No, so the definition of perfect secrecy it says no matter which message you choose, but it's only one message. You cannot use it again. We have other definitions in cryptography that talks about multiple message security, but they are more complex. So
this is interesting. Oh, I see. So you're saying there is basically you're saying you're only allowed to sample the message once, whatever your prior distribution is. And as soon as you sample it a second time, you better generate a new key.
Yes.
For the one-time padding. I see. Now, okay, I didn't realize that, but then I'm going to guess now, and I obviously didn't read your entire
No,
book,
of
but
course.
but there must be an extension of this where you because, for example, I as far as I know, my keys aren't updating all the time. I sort of generated a key once for all time. Yeah, okay.
That's why we need the cipher conjecture. This is basically why all of cryptography relies on P different than NP, because one-time pad is extremely restricted. You have to generate a new key for every message, so it's extremely restricted, and that's why when the KGB used it, they eventually did reuse the. That's why it's so tempting to reuse the key, but it's then all of your security guarantees go out the window. And this is exactly what the KGB did. They reused the keys, and then they all of this hundreds of KGB agents got caught because of that. And then and basically there is an impossibility result. There is a theorem that says that if you want perfect secrecy without making any computational assumptions, then this is a necessary condition. Then the one-time pad is optimal. You cannot reuse keys, and the total size of your messages, you can also generalize it to basically the total entropy of the messages needs to be smaller or equal than the total entropy of the key.
Okay, I think I see what's going on now, and it's obviously clear for this very explicit example. The problem with sampling multiple times is that essentially you can figure out the key coordinates in this case just from the statistics of each entry, right?
Yes.
Yeah, I see now. I see.
Yes. So basically, exactly, because the messages itself, like we said, there is some known prior distribution on it. So suppose you knew that the messages are, say, 60% likely to be zeros and 40% likely to be one.
Right.
So once you get multiple times that you're using coordinate one in the key, then you're basically getting a lot of statistics, because you know that 60% of the time this is zero. So 60% of the time you're going to see some bias towards that the actual value of this coordinate.
That's right.
So basically, this is why one-time pad is such a pain and it's not really used, because you're right. This is not what what we do now is, we exchange, we have some key like that is maybe 256 bits, and we are using it to encrypt many messages, and because of that, we really have to move to computational definition.
I see. Okay, yeah. Let's see. So, yeah. So, okay, yeah. A lot of forks in the road here. So, I guess So I think the next thing is to do the computational modification of this, I guess.
So maybe we could say that, So the one-time pad is like, the one-time pad is not practical because it really needs a fresh key for every message, and the total number or length of keys is as big as the message. So we could hope to improve it, but then there is this impossibility theorem that Shannon also proved, that basically the simplest version of it is simply that there is a theorem due to Shannon that there does not exist a perfectly secret encryption with say a key N and a message length L, which is more than N+1, let's say, or generally larger.
Shannon's most famous work is in information theory in terms of introducing Shannon entropy and things like that. This work in cryptography was that, I guess, after, before, around the same time? Do you know?
I think it's around the same time, and some of it you can kind of phrase these things also as it's kind of related. So you can phrase these things also as you can phrase these as some entropy conditions. So you can also give a kind of more general statement that the entropy of the key must be at least as large as the entropy of the message.
Okay, all right. Okay, great. All right, please continue.
Yes, and in some sense, if you know information theory, then if you know information theory, then in some sense you can prove this with information theory by basically saying there must be some there must be some mutual information between you can prove that there must be some non-zero mutual information between the ciphertext and the messages.
I see.
So
Okay.
you can use information theory. It will be something like I think this is basically what we could say is right. So we look at the mutual information between Y, the ciphertext, and the and the say X, the message. Right, and that basically there are like three sources of randomness. There are say two sources of randomness here: the message and the key. Right, and we know that because you can decode, we know that. So this basically we can write it as right the entropy of. So
I'm going to guess. I don't have much intuition for these inequalities, but I'm guessing something like the conditional what entropy of x given y should probably still be x is my guess.
Right. So
Something like that, right?
so basically want to say the right. This is usually I think we say the conditional. Right. Okay. Yes. I think this is basically what we say. This is the equality.
Okay.
Mutual information of y given x is the entropy of y minus the entropy of y condition on x.
Okay.
Okay. Now this is because you can decrypt. This has to be at least the entropy of x.
Okay.
Because you can decrypt, right? So y has to contain all the information about x. And the only source of randomness after you condition on x is the key. So this has to be at most the entropy of the key.
Okay.
So this has to be, so if the entropy of the key is less than the entropy of x, then this is positive. So there is mutual information between the ciphertext and the message, which basically breaks the notion of secrecy.
I see. Oh, nice. Okay, beautiful. All right.
Yeah. So basically, this is yes. This is I think the information theoretic proof of Shannon's. And yeah. Okay. So this is not an accident that he was thinking about these kind of things at the same time. Basically, this kind of impossibility result basically says that the notion of perfect secrecy is maybe too strong. And the way to to bypass it is to move to the computational definition. So to say, okay, we could potentially have an encryption, and we could potentially, we could have an encryption with key smaller than a message, but as long as an adversary would need to expand maybe exponential amount of computation in order to gain an advantage. So this brings us to the notion of computational secrecy. So we'll just kind of recall that, say, perfect secrecy is that basically for every pair of messages x0, x1, we said it's equivalent like for two messages. And for every function if, let's say from 0, 1, and star like to 0, 1, the probability that if we choose B at random from 0, 1, if we choose the key at random from 0, 1 to the n, that if, let's call it if, so it's not confused with the encryption, if of ek of xb, the probability that is at most half. I wrote here the definition. I wrote it slightly differently, but it's in equivalent way. So basically, I'm thinking of the game as you choose, there are two messages, x0, x1. You choose B to be at random either 0 or 1. You give Eve an encryption of either x0, x1, and then Eve needs to guess whether it's 0 or 1. Right, so this is the definition of perfect secrecy. And now we want to change to a definition of computational secrecy. So I'll just write the definition. We could go through the process of Socratic dialogue, but maybe it will take us a lot of time. So let's kind of write the definition.
Yeah, sure.
So the definition is basically the following thing. It's so computational. So I'll start it with a little bit, so computational, we're saying not for every function if, but for every efficient function. And now you get into computation complexity. What does it mean to be efficient? And let's just say for the purposes of this podcast is that, say, this is at most 2 to the n over, I don't know, 10 Boolean operations. So if is can be implemented by some circuit with, say, AND, OR, and NOT gates, and at most, say, 2 to the n over 10 operations or something like that.
This strikes me. So n is the size of the n is the key parameter, right?
Yes, not the 10, like just let's say 2 to the, I don't know, n over 2, whatever. Yes.
Okay, but this is still somehow exponential in n. I thought I'd see some polynomial condition. I'm a little confused.
So in theory, so this is a little bit where there is a little bit of a difference between theoretical cryptography and practical cryptography, and I'm here for this podcast. I'm kind of thinking more of the practical version.
Okay.
So in the practical version, when you're saying something like your key gives you 128 bits of security, you really want 2 to the 128 operations, because polynomial is kind of not exactly well defined. What do you mean, like 128 to what power? 3, 5, 10? So you kind of want to make things concrete.
I see. So you basically want something to supersede all polynomial complexity, but still be sub-exponential with regard to the 2 to the, like, the true exponential, right?
Right. Or maybe, I mean, you would have loved if you could get better than 2 to the n, but you can very easily show by brute force more than 2 to the n you cannot hope for, because you can always do brute force attack and enumerate over all possible keys. So you would like to get as close to that as possible. So the n over 2 here is just kind of, I mean, I put here n over 2. You could have put here 0.9n or something like that, but it's some kind of
right. Basically, you just want some function such that when you divide it by 2 to the n, it goes to 0 as n goes to infinity, something like that.
Right. You want it to grow very fast. To grow. I mean, maybe in practical terms, that if n was 256, then it would be big enough that you don't have to worry about it as the user of the encryption.
Yes, I see. Yeah, you want it as large as possible without being
without the definition being impossible to achieve.
Yeah, that's right. I see. Oh, I see. This is more about practicality than any notions of what was it, like negligible. It's really more about, I just want something that grows very large but not too large, so it's not 2 to the n. Yeah.
Yes. And it turns out that you also have to add like some kind of again, like just put some number there, but
sure.
So you need to allow so basically so basically you need to allow for there is always an exponential there is always 2 types of attacks. One is that you run in time 2 to the n to just enumerate over all possible keys, or you just guess a key and you have like some 2 to the minus n advantage over the
that's right.
the trivial. So we need to allow for both of those things. But it turns out that under some computational complexity assumptions, once we allow for both of those things, then as far as we know, it is possible to achieve an encryption where the key is much, much shorter than the message.
I see. So basically, it just to reiterate what you just wrote here. So this is, you could think of this as like the edge you would get from just brute force or lucky guessing, right?
Yes.
Brute force.
Yes. Maybe this is lucky guessing, like this is lucky guessing, and the thing on the left is the brute force.
Ah, I see. Okay. Okay, sure. So this is that one. Okay.
Right. So if so we kind of have to, because of Shannon's impossibility theorem, we kind of know that if we had no computational constraints, then we could never hope to achieve an encryption scheme with key shorter than the message. And you can show that basically if the key is shorter than the message, then you can always get some advantage by lucky guess, or a very big advantage by brute force.
And yeah, and the name of the game is that you allow this relaxation to get around this impossibility theorem, but
yes,
where you win is because n is a parameter here for sufficiently large n, it becomes infeasible to break the encryption system.
Right, and here is also like the magic of exponentials, that for kind of moderate n, so you could have a key that is just on the hundreds of bits, and you could get something that is secure, that as far as we know, even nation states cannot break.
Okay, right. Well, conditional on P versus NP.
Yes, conditional on yes, on conjectures that are even stronger than P, different from NP. So maybe we should try to say what's the goal. So this is a relaxation of perfect secrecy, but this relaxation turns out that under assumptions it buys us a lot. And it also kind of introduces us to the way things always are done in cryptography, where there is always a security parameter, which is the length of the key. And security is always quantified as some function that improves with the length of the key. And generally, there is a trade-off where basically the bigger the key, the more expensive it is for the honest users to encrypt and decrypt. But also the more expensive, the more infeasible it is for the adversary to break the encryption. But the beauty of exponentials is that the gap is huge. So you could have potentially an encryption scheme where the honest users can do it in microseconds, but the adversary would require more than the age of the universe to break. So we had the definition of perfect secrecy. So this was a definition. We have a construction, a one-time pad. We have a problem that the key, the length of the key needs to be larger, at least as large as the message. And another way to say it is also that we cannot really reuse the same key for many messages. And this is a big problem for using it. And we have a theorem that basically says the problem is inherent. That you cannot avoid this problem as long as you have the definition of perfect secrecy. So now we move to the computational domain. So we have a relaxation of the definition, which is computational secrecy. And then we'll see that there is a construction which we can think of as a de-randomized one-time pad. And in practice, it's also known as just a stream cipher. We can see that for this construction, we can have the key to be much, much smaller than the message. And generally, in practice, keys can be on the order of 128 to 56 bits, and the message could be in the gigabytes or terabytes. And we have and there can be a theorem that if there exist secure pseudo-random generators, then you can have a secure de-randomized one-time pad. So so basically, by moving to the computational secrecy world, we need to, if we're willing to live with the computational secrecy, which is really as good for all practical purposes, because no one can, even nation states cannot do 2 to the 128 operations, and even like, let's say, the number of flops in training GPT-4 is, I think, no one knows exactly, but it's at most 10 to the 25, which is less than, I guess, I don't know, 2 to the 70 or something like that. So 2 to the 128 is way beyond anything that Moore's law will ever get us. And not to mention 2 to the 256. And so computational secrecy is not really a problem. And now the thing that we, so giving up on perfect secrecy to computational secrecy is not really an issue. The other thing that we give up on is on Shannon's theorem was unconditional. The one-time pad is perfectly secret, period. Here we'll have to make an assumption. We'll have to make a computational assumption that pseudo-random generators exist. And that's life, because we need to make at least the conjecture that, as you mentioned, that P is different than NP, and for all of this to work.
Yeah, maybe just let's unpack this a bit. So, you know, writing the precise definition of a pseudo-random generator is a little bit involved, but it's easier to kind of say in words intuitively. I mean, basically, what a pseudo-random generator is doing is it's generating numbers that are computationally indistinguishable from a random sequence.
I think I'll do kind of proof by picture, definitions by pictures, and proof by picture.
I think that's appropriate. Yep.
So the definition by picture of a pseudo-random generator, so it is a function, so that say maps 0, 1 to the n to 0, 1 to the L, where L is larger than n. When we think of the input, we call it a seed, and the output is just output. So if we draw, we can draw a pseudo-random generator. We can think of it as, this is G. It has some input, random seed S, or maybe we'll call it K, thinking ahead. And then there is this output, G of K, right, of length L. And the kind of the security definition is basically that for so if we have some algorithm, distinguishing algorithm, and with probability half, it gets G of K for random K, and probability half, it just gets a completely random Z from 0, 1 to the L, then it cannot guess which is the case, again, with probability better than half plus something like that is, say, negligible or exponentially small. And D is itself, we need to assume that it is has less than, I don't know, 2 to the n over or 10 operations or whatever, 2 to the n over 2 operation. Some number. So basically, the definition of a pseudo-random generator, this actually can be, I mean, it's a by picture definition, but it can be made into math pretty straightforward, is that you output something that for every circuit that run in, say, less some exponential size, they cannot get better than an inverse exponential advantage in guessing whether the output was completely uniform or the output is pseudorandom. It comes from the pseudorandom generator.
Actually, now I look at it, it is a little surprising formulated this way that this definition even works, because the target space is larger than the source space, right? You have an injective map. Now the uniform distribution on L-bit strings would be supported on all those strings, but yes, you can't actually achieve that using the map G. So it looks a little pathological when you look at it, yes, right?
So indeed, it is a case that you have to make computation assumptions. So
of course,
if you were able to say, so this is actually like a great point that you're making. So one way to think about it is that you have the space 0, 1 to the L of all possible outputs. Mm-hmm. And you, the space of G of 0, 1 to the N, the outputs of the pseudorandom generator is kind of a tiny fraction of this space. Mm-hmm. But the point is, I mean, here I kind of draw it,
right.
Draw it like it's in one region, but it kind of generally it will be kind of distributed all over the place.
That's right. It's like this dust that's uniformly everywhere. It's maximally uniform as it can be.
Right. And the idea is that that somehow computationally simple classifiers like this D. So if kind of D then the fraction of the overall space that say D outputs one of on and the fraction of the blue points, these G of 0, 1 to the end points that D outputs one will be the same.
Basically, D doesn't have enough resolution, so that even though you have this dust, it's spread about so uniformly that D just doesn't have the resolution to distinguish between that dust and really sampling everything, right?
Yes, that's a nice way to think about it. Yes, so statistically, these are very far probability distribution. In total variation distance, in any kind of measure, statistical measure, the pseudorandom output and the uniform output are very, very different. But for computationally bounded observers, they look the same. Mm-hmm.
Okay, great. Yeah, which is kind of in contrast to this very intuitive picture of a pseudorandom generator. It's just literally randomly generating
right.
Digits, which is like intuitively you can do that, but it's just I just noted that when you wrote it this way, just like wow, that seems a little quite strange that you could actually satisfy this property. Anyways, okay, I'm convinced.
Yes, and this is indeed like the magic of this is why we don't know how to prove that P is different from NP. That this is like yes, it's you know it's a very strong kind of object in some sense, but
let's see, is this I don't know, equivalent to sorry, yeah, is this like what what's the right, like NP complete, NP hard, what's the right phrase?
I think the right way to think about it is actually NP easy in the following sense. If you had an algorithm for solving if P equals NP, mm-hmm. then in some sense every problem that for which you can certify a solution, you can also decide it. So in particular, given a point, say Z in 0, 1 to the L, you can certify that it is in the support of the pseudorandom generator by giving the K such that Z equals G to the K. Mm-hmm. So if P was equal to NP, then you would have also been able to tell apart to figure out whether, given a point Z, whether or not it is in the support of the pseudorandom generator. And if you could do that, you could break the pseudorandom generator. Mm-hmm. So basically, you can prove you can basically prove that if P equals NP, then there does not exist pseudorandom generators.
Okay. I was trying to. Well, the content of my question was whether if you can prove this PRG conjecture, could you say something about P versus NP? You're saying, but yes. PRGs too. Oh, okay.
That's just the contrapositive of what I just wrote. So if P equals NP, then they do not exist PRGs. So therefore, the contrapositive, if they do exist PRGs, then P is different from NP.
I see. I was just trying to figure out. Okay. The real content of my question was to what extent is there an equivalence here? Like, is P versus NP kind of just as hard as this conjecture, or but you just said it was like easy?
So there is actually there is a wonderful survey of Russell Impagliazzo that he wrote in 1995, where he basically constructed 5 different worlds of the status of computation complexity problems.
This is the source of your recent blog post with Scott. Yeah, okay.
Yes.
Okay.
So basically, these are kind of increasingly stronger conjectures. So you can have one world which you call algorithmica, where P equals to NP. But you could also have this world which he called kind of heuristica, where P is different from NP, but all average case problems are easy. And in this world, there would be no pseudorandom generators. And then the world where pseudorandom generators exist, he called it mini-crypt. And then you could, and then you could still have like that. Maybe pseudorandom generators exist, and public key cryptography doesn't decrypt when it doesn't exist. So he gave the name for the world where public key cryptography exists, cryptomania.
Okay, I see. Okay, I'll need to look at this paper. I'll learn a lot from it.
Yes.
Okay.
There was a recent Quanta, there was a somewhat recent Quanta article about these 5 worlds. So. Okay. I think we linked that to that from our blog post with Scott.
I see. Great. So we have this PRG, and the point is, this PRG enables one to have the computational secure encryption scheme, right? And it's basically just looking ahead. It sort of allows you to generalize the one pad idea in the right way.
Yes, the one pad, exactly. So basically, once you have this, it's fairly straightforward. So if we have a key K, we can feed it into a PRG, G, and we get this Z, which is G of K. And then if we have a message X, we can take this message X, XOR it, and now this will be the encryption. So the encryption with K of X will be G of K XOR X instead of just K, XOR X instead of K XOR X. So basically, we could say if you had a pseudorandom generator that can take a seed of say length 256 and convert it into an output of length 1 million, then now you can encrypt a message of length 1 million by doing this. Now, the way people do it in practice is that they don't apply the pseudorandom generator to get the output all at once. Rather, the way they kind of do it in practice, they have these pseudorandom generators that can give you pieces of the output. So rather than thinking about it as if you get a seed and then you get a huge output, you think that you get a seed and then you can generate parts of the output on demand as much as you want. And so you basically have kind of an endless stream of randomness. And so the sender and the receiver basically have, by exchanging the key, the same seed, they have 2 copies of the same stream of randomness. And whenever you want to send a message, you basically take the unused part of the stream, because it's still like a one-time pad. You need to use a part of the stream that you haven't used before. You XOR with that and send to the receiver, which is why in practice they call it a stream cipher.
So this solves the problem of reusing keys, right? Because you're basically updating your seed every time you go back and forth.
Yes, so you can think of it as updating your seed, or you can kind of conceptually think of it that the seed could conceptually, you can think of it as staying the same, but but you never reuse the output, right? So every time you take a fresh part of the output. Now in practice, the way they typically do it is you're right, like they have an initial seed, and every time you want to generate an output, you generate basically 2 things. One is the output, and the other is an update to the seed. And now you use it again and again, and now you can basically use it as much as you want.
Yeah, and this is pretty amazing, because if you think about it, this is one way to think about this is that it's a compression result, because basically you've compressed this really long string that you're doing the one padding into this very small key, right?
Yes.
So it's the same idea. It's just you're just compressing the one-time pad into this key.
Yes, and in some sense, one way to think about it is and this is also this content of the theorem that we have in the notes, that once you kind of used computation to somehow evade the laws of statistics, like generate a distribution of, say, entropy n-1 that behaves as if it has an entropy n, you can reuse it and break the laws of statistics even more. And suddenly you can take a 256-bit long key and pretend it is like and use it to generate pads of length of gigabytes that behave as if they're uniform, even though they have basically almost no entropy compared to the length, but it's still indistinguishable.
Yeah, okay, this is, I mean, we can go into many more details, but maybe in the interest of more breadth instead of depth, I think this pretty much summarizes kind of the key highlights of private key cryptography, right?
Yes.
So we defined what a valid encryption scheme was. We eventually found a good definition, I guess, due to Shannon, right? And then now we've validated that this whole setup works, provided this PRG conjecture holds, which also assumes P is not equal to NP, correct?
Yes.
Maybe what's next then is public key cryptography, right?
Sure.
Yeah, okay.
So the main kind of problem with private key cryptography is that you still somehow need to share the key.
That's right.
I don't know about you, but I've never been to Amazon headquarters to go and exchange a key with Amazon so I could purchase online there. The notion of exchanging a key, that might work for spies that, they get a key when they, when they go off to the mission, but doesn't really work on the internet today, where we often want to communicate with someone that we've never met in person before. We don't have this out of band channel of communication to exchange the key. And it was kind of obvious, I think, to everyone that this is inherent, that you cannot have secrecy if you didn't exchange a key, until a few people started to think about it harder and realized that there isn't actually a mathematical proof that this is inherent, that this is impossible. And several different people had the same thoughts. There was some people in James Ellis in a British intelligence agency, GCHQ, thought about this kind of thing and realized there isn't any possibility result. Diffie and Hellman thought about this, and Ralph Merkel was an undergraduate, also thought about this. And as I mentioned in my book, he wrote a project proposal with this idea, and basically his professor said, no, this is obviously nonsense, try to do something else. And he then tried to submit it to the communication of the ACM, and the review says, experience shows that it is extremely dangerous to transmit key information in the clear. So, so the notion of public key, that seems like a contradiction in terms. The whole notion of a key is that it's secret. How can it be public? So it's quite interesting, this notion. So maybe we can try to see what does it mean to be a public key encryption.
Sure.
Right? So we have again Alice and Bob. Alice has a message X that she wants to send to Bob, and intuitively people think it's kind of obvious that the only way she can send a message to Bob is they have to share the secret key. But in public key encryption, we say, okay, actually, Alice is going to use the encryption algorithm. Bob is going to use the decryption algorithm. What they thought is, what if the encryption algorithm and the decryption algorithm don't actually need to use the same key? So the idea is that Bob can generate a pair of keys, E and D. So E is the encryption key, and D is the decryption key. And now Bob can send to Alice the encryption key E, And Eve also will learn E. So
right. This is the public key by definition, because that's
yes,
the one
this
you're
is, so
sending
E
out.
is public key because you're sending it in the clear. So Eve also sees that. And now Alice is going to encrypt, send an encryption with the key, with the key, with the key E, and Bob will decrypt with the key D. So now the condition is that, say, for every X, encrypt, if you decrypt with the key D, encrypt with the so you decrypt what you encrypted, then you get back X. And now the security condition is basically the same as before. You still want computational security. We still want that for every pair of messages, Eve cannot distinguish, say, if the message was X0 or X1. Where now the twist is that Eve cannot distinguish even when she's given the public key, because it is public.
Right. Yeah, and D, of course, is therefore the private key.
Yes.
Right. And just to state this in words, basically, this allows anyone to communicate to Bob, but only Bob can read those messages.
Exactly.
One of the nice things about your book is you give a lot of intuition and colorful commentary. I didn't quite catch the intuition behind why people thought this was possible, because when you look at this, it's just not at all obvious why this should be true. It's it's like a door that works with two different keys or something, which is like I don't know about doors, but that doesn't seem I've never seen a door that works that way, right? So yeah, can you give some intuition like why you should even think this is possible?
Right. So I think that first of all, I think intuitively it should be impossible. And I do believe that if you read some of the thoughts of if you read some of the thoughts of Alice, etc., I think part of it was people trying to first think about it and then try to prove that it's impossible, and then realize that they cannot prove that it's impossible, and then maybe they kind of reshaped their intuition and started adjusting their intuition because it's definitely like I said, I mean, this is not something that people guessed. It's not like heavier than air flight or going to the moon. It's not something that people said, here is a dream that we should do, and we just don't know how to do it. Like most people just thought it's, if they haven't given it a lot of thought, they just thought, okay, it's obviously impossible. It's like, so there is no intuition immediately. There is no intuition why it should be possible. Once you start thinking about it, maybe the way to think about it is one of those locks that you click shut, right? So there are these locks that you don't need a key to lock them. You only need a key to open them.
Yeah.
So,
Actually, it's a great example. It's sort of like the post office drop box, those blue boxes outside. Yes. Like you open the hatch, you put your box in, and you close it, you can't open it again because it's too far down, and only the mail person can open it, right?
Yeah. Yes, exactly. So there are like these kind of things where like there is a trapdoor to do it in. So there is an easy way to do something in one direction, but to do it in the other direction, you need something else. Like so you need maybe the key of the mail person, or if you have these locks that you push the click to shut, then yeah. So once you think about it, you see, okay, the encryption and decryption, they don't have to be symmetric. It doesn't have to be the same operation.
That makes a lot of sense now, because we've already, the whole name of the game with P versus NP is it's hard to do things one way and easy the other, right? And the easy should be the encryption and the hard should be the decryption. So phrased that way, now it's like more plausible, right?
Yes. Yeah. So I think eventually, like the first intuition is that maybe it's impossible, but then you shape your intuition, and eventually you find a different metaphor, and you figure out, maybe it is actually possible, but it is much more subtle than private key cryptography. In particular, there are like a bunch of constructions for pseudorandom generators, and in generally, like they kind of looks like like, you just put a bunch of logical operations on top of it, and you put enough of them, and you scramble things enough, and eventually you get something that's probably a secure pseudorandom generator, unless you kind of made some mistake along the way. But with public key, you really do need to use some math, and there have been very few actual constructions to achieve this idea.
At least the simplest version of an instantiation of public key cryptography, it's pretty basic number theory. It has to do with exponentiation.
Maybe I'll just say, like, at a high level, what people have used. So there generally been, in some sense, two main themes. Like, so there has been a kind of number theory construction, which use either integer factorization or a discrete logarithm. So basically, like every other encryption, you still need some kind of problem that is computationally hard. So integer factorization, there is this problem that, say, you take two primes P and Q, and you map them to N, which is P times Q. So it's easy to, this side is easy, but reversing could be hard. And again, we have to be precise what is meaning it hard. Like, we all actually learned how to factorize numbers in grade school, but the algorithms that we've learned, it basically scales. So if you have a number n, it kind of you do a for loop that goes all the way to n, or maybe if you're a little bit clever, square root n. But if n is, say, 1,000 bits, if n is 1,000 bits, then square root n is like 2 to the 500, and that's like so that's not something that you can do. And there are better algorithms, but generally we don't like, the algorithms take time that is exponential, not in the number itself, but in the number of bits to describe the number. And discrete logarithm is, again, like something like you take some number g and some number a, and you and maybe some prime p, and you look at g to the a modulo p. And again, this part is easy, but reversing this is hard. Say, given g and g to the a, we don't know how to do the log and get a back. So these are two problems that have been kind of one source for public key encryption. So this is Diffie-Hellman and an RSA. And there is elliptic curve cryptography, which is basically a version of discrete logarithm. And then the other problems were based on error correcting codes or lattices. And generally, these are things basically of the form, say, you take X and some code A, and you encode this and noise it up. So this part is easy, and so, under some assumptions over finite fields, over certain versions, decoding could be hard. So so given say A and AX plus E, when you're over some finite field, then it could be hard to decode to remove the errors.
Okay. Yeah, I guess the reason I wanted to gloss over this, not only because I think it'd be nice to talk about some concrete applications, because we've been talking very theoretically, but also it's you can go on Wikipedia, look up the algorithm, you can write some formulas based on arithmetic. It's not particularly deep. It's just you can see it, right? But yeah.
But the thing I should mention is that like, and especially since you talked to Scott, is that basically if scalable quantum computers get built, then this left side is done, it's broken, and we are only left with the right side.
Oh, I see. So Shor's algorithm would nullify the left-hand implementation of public key cryptography, but we're still okay. So it's not that much of a Well, okay, we have a backdoor to this security breach, basically.
Yeah, so this is what's
Necessary.
known as, so basically this thing on the right is what people call post-quantum cryptography.
Ah, okay.
And we're lucky we have it, but it is a little bit uncomfortable in the sense that if someone discovers an algorithm, either classical or quantum, for this decoding problem, then that's essentially it.
Okay, I
We don't
see.
have right now, we don't really have other candidates. People have been trying to propose some things, but most of them have been broken. And so generally we don't have like a very reliable candidate apart from this.
I see. So I think it'd be good to take stock of what we've accomplished, which is a lot,
Yes.
and just talk about some applications. We could just be very cartoonish about it because we've
Sure.
gone into a lot of detail. I mentioned a few things, and yeah, feel free to talk about them with any level of granularity. But you know, Bitcoin is a topic of the day. I mean, it fluctuates in terms of its hotness, but it's still in the conversation. You know, maybe Bitcoin. Maybe any of your thoughts on like deepfakes and authenticity, things like that, and whatever interests you in machine learning. Yeah. So. Yeah.
Sure. So maybe we can, we can chat about those things and maybe at kind of a higher level.
Sure.
So,
yeah. Indeed.
So the general idea of Bitcoin is currency which is decentralized. So there isn't one authority that says who owns what. Then you need to solve a problem that in computer science is known as the consensus problem. So you need to agree on who owns what. So you can have some kind of a currency or any type of shared data structure. And in the distributed systems, there have been several solutions to this problem. But generally, the way these solutions worked is they said, okay, we have n agents, and as long as, say, a majority of them are honest, then we can achieve some consensus. And that's great. But if you have a decentralized system and everyone can sign up like and open 1 million accounts, so how do you decide what is majority? And the really nice idea in Bitcoin is they said, you know, so what we'll do is we'll say a majority of the computational cycles. So in order to vote, you need to spend some computational cycles. But how do you prove you spend some computational cycles? This is where basically crypto comes in. And generally, what they said is, you know, you can set up these. So we said in cryptography, you can set up tasks where you have some parameter n such that the effort to break the task is 2 to the n. And typically, we set up this n so that it's so big that no one would ever break it. But Bitcoin, and indeed in this, there was some previous work that tried to use this idea also from proof of work by Dworkin Naor that for spam email. The idea is rather than set n to be huge, set it exactly at the right level. So the idea of Bitcoin is that you basically set these kind of computational puzzles where you scale up the n to the right level so that solving this puzzle will be exactly hard enough. And in some sense, then this is basically how you kind of vote on what is the ground truth on, or in Bitcoin is what block gets added to the blockchain. So now there is like a lot of you know, additional complications, and Bitcoin uses also signature schemes. And so part of this, we didn't talk about digital signatures, but basically this is in some sense what is your identity in all of those in these cryptocurrencies, which again you can think of it as a computational puzzle. So if there are no identities, how do I prove, what does it mean that I'm the owner of a certain coin? I'm the person that has a secret key that corresponds to a certain coin, and typically it's a signature key, not an encryption key. So basically, these cryptocurrencies use cryptography and particularly computational puzzles to get around the paradox that they're trying to solve, which is how do you do a decentralized mechanism where you need a majority, but a majority of what? And then there are these two variants, and both of them use cryptography. So one variant is proof of work, where basically every cycle gets one vote, but of course it has a lot of its own problems because you basically have to burn a lot of cycles for no useful reason, and so it's not good for the environment. It's also not good for the efficiency of the system, and the Bitcoin system is famously inefficient. I forget the numbers, but probably Visa can process, I think probably, I don't know, 10 million times as many transactions per second as the Bitcoin network or something like that.
Actually, just to make this concrete, how does this concept of this proof of work solve the double spending problem? Let's just drop it.
So you need basically you reduce double spending to the problem of consensus on ledger, right? So if basically let's imagine that every key had every coin. Say all the coins were atomic. Like look at the
sure.
Smallest unit. This is not exactly how this works, but let's say you had like a tiny unit. They call them satoshis, and suppose each one of them had its own identity. And basically there was a ledger that basically said, Alice owns coin number 7895. So there was this ledger, and then basically says Alice gave Bob coin number 7895. Now, if Bob comes to you and wants to pay you with coin number 7895, you can go and look at the ledger and or the blockchain and say, okay, yes, Bob really does own this coin. So there is no double spending. Yep. So you basically reduce the problem of double spending to the problem of having an online ledger that everyone, and again, it would be trivial if there was some website that we all trusted and would have this ledger in it. But the whole point of Bitcoin is that there isn't.
So what happens if, say, Alice tries to give Bob coin 7895 and Alice tries to give Eve coin 7895? What is
so as long as Eve and Bob both agree on the copy of the blockchain on the ledger, then they can both see who owns this coin, and basically the moment Alice say gives it to Bob, then she hasn't given it to Bob. The coin hasn't been received until that transaction has entered into the blockchain and was registered. So it basically is a little bit like the way we sell houses, right? If you want to sell me, suppose you own an apartment in San Francisco and you wanted to sell it to me, then there is a deed in the San Francisco city office that tells who owns that apartment. And to sell it to me, eventually the deed has to be transferred, and then I'm registered as the owner in the San Francisco in the San Francisco office. So this works well when there is a centralized office that says who owns what. And the idea of Bitcoin is we replace the centralized office with a decentralized blockchain. And conceptually, you can think that when someone proposes which block to add to the blockchain, then we do an election and we vote on it, where each computational cycle gives you one vote. The way it actually works is a little bit more probabilistic, where basically you can say that each cycle kind of gives you like a lottery ticket, and the more cycles you have, like the better chance you have to win, and the winner of the lottery ticket is the one that gets to choose which block to add to the blockchain. Every time you apply a hash function, it's like buying a ticket, and if you get like an output that starts with many, many zeros, then you won.
I think we said enough about Bitcoin. Why don't we maybe wrap this up with maybe some interesting machine learning thoughts you might have? Or I know on
Sure.
my end, I'm curious. I think actually on my end, and you could comment whatever you're interested in too. But on my end, I was much more optimistic about the future, having learned about cryptography, because I was thinking, like, I think many other people who might not be well informed, like, especially for me in cryptography, which is that, machine learning, the future, we're going to just be flooded with deepfakes because look how much better they're getting, and how we're going to trust anything we see. And we didn't get to talk about it, but with the digital signatures, which is a way of giving authenticity through public key cryptography, does that basically solve, in some sense, the issue of deepfakes? Because in a world where everyone has to sign things, so right now it's sort of, it's actually funny. We live in a world where, because deepfakes are an emerging technology, or generative AI is an emerging technology, you might want to watermark those to know that they're fake. But there could be a future in which the reverse is true, in which you want to authenticate everything which is authentic, and then everything which is not authentic is fake, just because now the ease at which it is to make fake things is so it's feasible. Like, anyways, does that seem like a reasonable future to you? And is that like the solution you might think of in terms of, like, how do we combat misinformation in the future? Just digitally sign everything.
This is a nice thing. I mean, I think to some extent it is like, I mean, I actually like this. Generally, crypto can help you a lot in provenance, like, and it can well be the case that, I mean, we already know about Photoshop and other things, but it can be with more and more deepfakes. It could be the case that if you don't have provenance, it's like with art, right? If you buy, like, if people have realized that there are some forgers that are really, really good at forging art. So typically, if someone comes and wants to sell you a Rembrandt, you want provenance. You want to know exactly where this painting was and how it got there, and you don't just look at it and say, "Ah, wow, it looks really good," because people have learned the hard way that you can forge these things. So it could well be the case that we would have this more and more with images, videos as well, where we want provenance. We want to know where this photo was taking place, and where and how did it get to the internet. And then and sometimes maybe it could be a problem, because obviously, like, I mean, cryptography, by the way, can help also sometimes with that. There is this whole notion of zero knowledge proofs, where you might be able, for example, to prove that a photo was taken by a certain device, but without revealing exactly the identity of this device. So there could be some kind of interesting cryptography where basically, suppose you're taking a photo of police violence, and the photo is authentic, but you don't want to sign it under your identity, that it could be traced to your phone. So there could be potential ways in which you could authenticate that it was taken at a certain time and place without revealing who it was that took it. There could be some very interesting cryptographic things to try to solve the problem of how do you simultaneously certify some facts about this without giving everything away. So I think cryptography can play a role in that. And by the way, I think already, in some sense, sometimes if it's actually, there was at some point, like, I think in Australia, there was a case where basically, I think judges tossed out some speeding cameras tickets because they used the wrong hash function or something. They used too weak of a hash function or something. So in some speeding cameras, sometimes they do already use some cryptography to authenticate that what they took. So yeah, I think that if we don't rely on our eyes to tell whether something is authentic or not, then it may well be the case that crypto can help us with provenance, and some fancy crypto can try to try to have the cake and eat it too, in the sense that both certify things and keep the privacy of the individuals that generated this image, in case that it's important.
So yeah, so long story short, is it based once you know enough cryptography, is it reasonable to be optimistic that we won't be society won't be collapsing because of deepfakes? We do have enough.
Yeah, I
Assuming
mean,
P again, assuming P does not equal to
yes.
NP,
Yeah, so I think
that
first of all,
society
I
won't
mean,
collapse.
this is a kind of like also an important point to say that all of these advances in deep learning, GPT-4, etc., have not touched cryptography at all. In terms of breaking cryptography, there's deep learning had zero impact on that. As far as we know, and there is no reason to say doubt the security of our encryption algorithms based on any advances in deep learning, etc. So I don't know, maybe it will change in the future, but so far as we know, AI can do a lot of things that humans can do, but humans cannot break encryption schemes like the AES, and neither can deep nets. And I think it's not, implementing new cryptography is never kind of simple. So I don't, it's not like a turnkey solution, but I do think that it's definitely something that could play a big role. And again, if we kind of move to the mode where everyone is suspicious about some text and images that, or videos that appear on the internet, if they don't have the provenance for it, then crypto can really help you with certifying provenance.
That's great. So it sounds like to me like there's a lot of AI doomsday people out there. It seems to me, based on what we've talked about, the real thing you should be scared about if you're a doomsday person is whether P is equal to NP or not, right? That's the real scare. If P is equal to NP, I feel like that's the doomsday scenario.
People could say, even without, breaking crypto, maybe, so I don't want to go into the whole, doomsday type of AI type of things, but yeah, I agree. Like in some sense, if P equals NP and someone bad discovers that, whether that someone bad is an out of control AI, or is it like some dictator or something like that, that's probably that's very, very bad, because a lot of our systems, like a lot of the security of our systems really trust cryptography. And I think the main thing you can think of, like just over-the-air updates, like suppose that you could forge the digital signature of Apple and send to people over-the-air updates to their iPhones that basically would make it into a listening device and send all of the information there you could wreak such havoc.
People are impressed about AI, being human level intelligent or mimicking humans. This security has nothing to do with that. It's just like I can't even authenticate anything or do any transactions securely. Yes. This is nothing about human level intelligence, right? Yes. So it's even more basic. Yeah, yes. That's what I meant. Okay, yeah. Do you have any, I don't know, final thoughts or anything else you wanted to talk about that might be interesting?
No, I think we made, I think we had like some good, yeah. I think we had some good discussions, and yeah. I mean, I do say that if people are interested in the kind of history of crypto, there is this book is kind of the older history, like the code breakers, and there is like I have it here. Like this one is a little bit newer. Is Stephen Levy crypto.
Okay.
That's and then there is my book for the more technical stuff. There is also a nice book by Katz and Lindell. So plenty of I think there are some nice Coursera courses by Dan Bonnet. So there's lots of room to learn more for people that want that.
Okay, great. Well, thank you so much, Boaz. This was really fun, and thank you so much for your time. It was great learning so much about this very exciting subject with you.
Thank you. It was fun.